Okay, in this video we're going to be taking a look at a few things. We're going to be looking at an introduction to limits, how to pronounce limits, what limits are in a sense, what a limit looks like algebraically, mathematically, then graphically. Then we're going to talk about average versus instantaneous rate of change. In algebra, you've been doing all average rates of change. In calculus, we're going to be doing instantaneous rates of change. So there is a difference. All right, so let's go ahead and get started. First of all, average rate of change. Let's just talk about that. So here in this first one, remember average rate of change, that's just average speed, that's distance divided by time. So if you want to know the average speed of something during the first 4 seconds of the fall, okay, so let's say this is in feet, just so we have labels. So this represents its height at any given time t. So during the first 4 seconds, we can find the average speed because it's just the distance. So it's the change in the distance over the change in time. So it's changing your y, how far it's dropped vertically, versus not as it doesn't move horizontally, but horizontally is your time axis. Because remember, if you graph this thing, it might look something like, that. So then your change in y is where it ended minus where it started. So y of 4 minus y of 0 all over the change in your time. So that'd be 4 minus 0. So then that gives you 16 times 4 squared minus 16 times 0 squared all over 4. Then on top, this is gone, and then you have 16 times 16, which is 256 over 4, and then that gives you just 64 feet per second. Okay, so then 64 feet per second, that's the average speed. To give you kind of an insight to what instantaneous speed, it's exactly what it sounds. It's the speed at some instant in the fall, like at 2 seconds or 2.13 seconds. It's at a specific time in that fall. That's the instantaneous speed. So that's what we're going to find. All right, so average speed. So now let's take a look at limits. This is a very, very formal definition. It's in your notes. I just wanted you to have it. Very formal definition of limits. Basically, this is what you have to be familiar with. And as you're doing these problems, I want you to just read them out loud to yourself, okay? The limit x arrow c, that's the limit as x approaches c. C is some constant. So it's the limit as x approaches c of f of x is equal to L. L represents your limit. So that's how you say it. The notation means that the values of your function approach some value like a y value. So L, if it's as x approaches a constant, then L is some y value. Okay, because you're sweeping the function from left to right. For example, if you take a look at this is just one that you have to remember. We're not going to go over the proof why this is true or not, but you have to remember. A lot of times, the very first thing that you want to do when you evaluate a limit is a thing called substitution. And you would take this value, c, this constant value, and literally substitute it in for your x. But you notice in this case, sine of 0 over 0 divided by 0, that's undefined. Okay, so it's not going to work. But if you look at the graph, so here's the graph, and so if you look at the graph as x approaches 0, what's your y value approaching? Right there, 1. Okay, so we know that the limit as x approaches 0 of sine of x over x is equal to 1. However, when we plug it in, substitute it in, it's undefined. Okay, and that's because there's a specific type of discontinuity of the graph, which we'll get into later, but that's called a hole. There's no value at that point, but there can be a limit at a point, even though there's no value at that point. And this is the most common, most popular example of that. So definitely put this in your toolkit. So put this limit right here. Put that in your toolkit. because it'll come up, or different variations of that limit will come up in the future. Now you have all these properties. I'm not going to go over them because they're very similar to the properties that you've seen before, very similar to basic properties of numbers. If it makes sense, if it walks like a duck, talks like a duck, it's probably a duck. So if it makes sense to you that this could be true because you've been, these properties of numbers have been pounded into you, then yeah, it's probably going to be true. All right. I'm not going to go over those. Look over those. Let me know if you have any questions in class. Let's do an example here. So you know that the limit as x approaches c, k is some constant. So c is a constant and k is a constant, but they are different constants. So the limit as x approaches c of some constant is equal to that constant. And the limit as x approaches c of x is equal to c. Use those properties to evaluate this. So remember, we're just using substitution. So we substitute c in for x. So you'd have 2c to the third minus 3c squared plus c, and then again, when you substitute in for a constant, the constant just stays the same. And then that would be your final answer. That's all that you can do unless you know what c is, but we don't in this case. So that's a basic idea behind limits. Again, the first thing you want to try to do is substitution. And again, here's just a formal definition, just want you to have it. It says if f of x is a polynomial, then the limit as x approaches c is basically plug that c value in. Okay, if this is just a regular polynomial, plug that c value in for all of these x values here. So plug c in for all of those x's. That's all that's saying. And then the second part, if f of x and g of x are rational numbers and you have a quotient of rational numbers and you're finding the limit, you would again plug those in there. So you plug c in for x for both of those, and then you would divide those. And again, as we saw on the sine of x over x, this bottom right here cannot be 0. If that's 0, then it's undefined. You have to take a different route to see if it's possible, which we'll get into later. All right, let's take a look at a couple examples here. The first one, just plugging it in. If you want to try this on your own, you can. It's not really that difficult because all you're doing is plugging 2 in for y. So you get 2 squared plus 5 times 2 plus 6 all over 2 plus 2. So that gives you 4 plus 10 plus 6. That's 20 over 4. And then that limit is 5. Okay, so as your y value approaches 2, or you can look at this as x, this variable doesn't necessarily matter. 9 out of 10 times it's going to be an x. Okay, it's at 1 out of 10 times when it really doesn't matter what that variable is, especially when you're not looking at it graphically, you're just looking at it algebraically. This one, however, we have to determine graphically and then confirm algebraically. I'm going to switch these around. We're going to do this algebraically, then confirm graphically. Okay, if you want to try this on your own, challenge yourself, go ahead. If you need a hint, I'll give you a hint. If you don't want a hint, go ahead and try it and then come back. But here's your hint. This sine of x, or this x plus sine of x over x can be broken up into x over x plus sine of x over x. Algebraically, you can do that. And keep this in mind because as we go through, do derivatives, integrals, limits, all of these things, this property, algebraic property, will come in handy lots of times. So with limits, you look at those limits back there, what you can do is, this is the addition subtraction rule, you can then separate this into two limits. So this becomes the limit as x approaches 0 of sine x over x, and the limit as x approaches 0 of x over x. Now you can evaluate these limits separately. So you evaluate this limit, then you would evaluate this limit, and then add them together. Evaluating this limit, x over x is just 1 over 1. So this simplifies to 1. So it's really just the limit x approaches 0 of 1. And remember up here, when it's a constant, it's just that constant. So this is just 1. So it'd be 1 plus. And we know what this is. Remember back the limit to remember, sine of x over x is a limit as it approaches 0. That's also equal to 1. So then that's 2. And again, we can look at this graphically. Here's our graph. Might be better looking at this. So this is what our function is looking like. And this is x plus sine of x over x. And as it approaches 0, you notice the y value is 2. But right at that y value, there is no limit. Try it in your calculator. Go ahead and find the value at 0, and you'll see that there's no limit there. It'll give you either, depending on your calculator, say undefined, or just will be blank, because there's a hole in the graph right there. Okay, so we have one more, and so this is taking a look at limits from more of the graphical perspective. So these points on the graph can have, one-sided limits. Or two-sided limits, doesn't matter. We've been looking at some that have two-sided limits, whereas like if you have a curve like this and you're looking at this point, okay, as x approaches that point from the left and as x approaches that point from the right, okay, let's say that this is point, we'll do point D, the limit as x approaches D from the left is equal to the limit as x approaches D from the right. Okay, so this is a two-sided limits. Those two-sided limits are equivalent. Therefore, the overall limit, like looking up in this definition, here are your two-sided limits. This is your left side because it's to the negative, and this is your right side because it's c to the positive. If your left and right side limits are the same, then that means the overall limits, the limit as x approaches D, exists. Okay, so we'll just put an L there. So if these are equivalent to L, then the overall limit. So there's three different types of limits. There's the left-hand limit, the right-hand limit, and if those are one-sided limits are the same, they're equivalent to the same value, then the overall limit, which is the third limit, is it exists. So looking at some of these, just go through. We can do one together. Just go, or whenever you're comfortable, try to do these on your own. Again, practice, practice, practice. Just don't watch these videos to get your notes done for the points, okay? Just practice on your own. That's how you're going to learn. So, pause the video, take a couple minutes to do these, and then come back and check your answers. Okay, looking at some of these, here's the answers. Just going to glance through them. Limit as x approaches -1. So first of all, find -1. That's here. Okay, so we're looking here. So x approaches -1 from the right. So you're approaching it from the right. What is your y value? Well, your y value is equivalent to 1. So that's a true statement. Here, the limit as x approaches 0 from the left. So you're approaching 0 from the left-hand side here. As it approaches 0, what's your y value? 0, so that's a true statement. The limit as x approaches 0 from the left. Here, we already know that it's 0 as x approaches 0 from the left. That's not true. Okay. Now, if there were, let's say, a C.1 question, the value of your function at 0, now that would be equivalent to 1 because there's a hole there, and that hole is brought up, and the value of the function is equal to 1, but the limit as it approaches from the left and then also the right is equivalent to y equals 0. And since the left and the right, so looking at E here, since the left and the right hand limits are the same, then the overall limit, because I say the overall limit because you notice it's x approaches 0, there's no plus or minus, the overall limit exists, so that's true. Okay? And then just looking at 1 and 2, looking at x equals 1, it has a one-sided limit. The limit as it approaches 1 from the left is equivalent to y equals 1. The limit as x approaches 1 from the right is equivalent to y equals 0. Okay, so you notice those left and right hand limits are not the same. Therefore, that overall limit does not exist. I know there's not that question. Actually, right here, the limit as x approaches 1 is equal to 0. That's false. The limit as x approaches 1 is equal to 1. That's false, because the left hand limit is 1 and the right hand limit is 0. So these don't exist. Okay, so if you have any questions on these, just let me know in class, but the main idea in this video was to understand graphically and algebraically how to find limits. This is the main ideas, and then also make sure you get that limit put in your toolkit right there. Sine of x over x as x approaches 0 is equal to 1. Put that in your toolkit, and I'll see you in class.